Male platypuses possess one of the most fascinating and unusual features in the animal kingdom: venomous spurs on their hind legs. This characteristic, rare among mammals, makes the platypus a unique subject of study in biology and toxicology. Below is a detailed explanation of the anatomy, function, venom composition, effects, and evolutionary significance of these venomous spurs. Anatomy of the venomous spurs, location and structure. Male platypuses have a sharp, hollow spur on the inner side of each hind ankle. These spurs are approximately 15 to 18 millimeters long and made of keratin, the same material as claws and horns. Each spur is connected to a venom gland, known as the crural gland, located in the thigh region. Their spur and gland together form the crural system. Connection to the venom gland. A duct runs from the crural gland to the tip of the spur, allowing venom to be delivered when the spur pierces a target. The spur is mobile, capable of being angled forward to deliver venom effectively during an attack or defense. Sexual dimorphism. Only male platypuses have functional venomous spurs. Females are born with rudimentary spur sheaths, but these lack venom glands and are shed early in life. This sexual dimorphism suggests the spurs play a role in male-specific behaviors such as competition or defense. Venom production and delivery. Venom gland. The crural gland produces venom, which is stored and secreted through the spur. The gland is most active during the breeding season, late winter to spring in Australia, roughly July to October, indicating a possible role in reproductive competition. Delivery mechanism. When a male platypus feels threatened or is engaging in combat, it can drive its spur into an opponent or predator. The spur acts like a hypodermic needle, injecting venom directly into the target's tissue. The platypus may wrap its hind legs around an opponent to deliver multiple spur strikes, maximizing venom delivery. Composition of the venom complex mixture. Platypus venom is a cocktail of proteins, peptides, and other bioactive molecules. Research has identified at least 19 different peptide fractions, including defensin-like peptides. Similar to those found in reptile venom, these peptides contribute to the venom's pain-inducing and tissue-damaging effects. Nerve growth factor, NGF. This protein may enhance pain sensitivity by affecting nerve endings. C-type natriuretic peptides, CMP. These contribute to cardiovascular effects such as lowering blood pressure. Enzymes and other proteins. These may cause tissue damage, inflammation, and other physiological effects. Unique to platypuses. Unlike snake or spider venom, platypus venom is not well studied, but it appears to be evolutionarily distinct, having developed independently in monotremes, egg-laying mammals. Effects on humans. Intense pain. The venom is not lethal to humans, but causes excruciating pain that can last for days or even weeks. The pain is described as immediate, intense, and radiating from the site of the sting. It is often resistant to conventional painkillers, including morphine, making it particularly debilitating. Other symptoms: swelling and inflammation. The area around the sting site swells significantly, often spreading to the entire limb. Hyperalgesia. The venom induces heightened sensitivity to pain, making even light touch agonizing. Systemic effects. In some cases, victims experience nausea, muscle weakness, or low blood pressure due to the venom's cardiovascular effects. Case studies. Reports of human venomation are rare but well documented. For example, a 1991 case involved a man stung by a platypus who experienced severe pain and swelling for weeks, with limited relief from painkillers. Another case involved a veterinarian who required hospitalization after a sting, highlighting the venom's potency. Treatment: there is no antivenom for platypus venom. Treatment focuses on symptom management, including washing the wound to prevent infection, applying local anesthetics or nerve blocks to manage pain, though these are often ineffective. Monitoring for systemic effects like low blood pressure, effects on other animals. Lethality. The venom is more dangerous to smaller animals such as dogs or other platypuses. In some cases, it can be fatal to small mammals or competitors, likely serving as a defense mechanism or a tool for establishing dominance. Behavioral impact. During the breeding season, male platypuses use their spurs in aggressive encounters with other males to compete for mates or territory. These fights can result in severe injuries or death for the loser. Evolutionary and ecological significance. Evolutionary origins. The platypus is one of only a few venomous mammals alongside certain shrews, solenodons, and the slow loris. The venomous spur likely evolved as a defense mechanism or a tool for male-male competition in the platypus's aquatic environment, where physical combat is limited by water dynamics. Ecological role. The venomous spurs reinforce the platypus's status as a solitary and territorial animal, particularly during the breeding season. By deterring rivals or predators, the spurs help ensure reproductive success and survival. Convergent evolution. The platypus's venom system is an example of convergent evolution, where unrelated species, e.g., snakes, spiders, and platypuses, develop similar traits independently. The presence of defensin-like peptides in both platypus and reptile venom suggests a shared evolutionary pathway for venom production. Interesting facts and research insights. Seasonal variation. The crural gland enlarges and becomes more active during the breeding season, suggesting that venom production is hormonally regulated, possibly linked to testosterone levels. Potential medical applications. Some components of platypus venom, such as peptides that affect blood pressure or pain pathways, are being studied for potential therapeutic uses, though research is still in early stages in comparison to other venomous animals. Unlike snake venom, which often aims to immobilize or kill prey, platypus venom seems primarily designed to cause pain and deter aggressors, aligning with its role in intraspecific competition rather than hunting.